This talk is about a geometric reformulation of the Riemann hypothesis. So consider MathCal I to be a compact two-dimensional stratified orbit space. We're going to obtain that by gluing four spindle orbifolds together along a common one-dimensional incidence stratum gamma. So it looks something like this. This is just a illustration of what it might look like. We're assembling these football orbifolds into the sort of complex, the object, the orbit space, or complex. And I have not shown the intersections in this picture, but here we have what I'm going to define as the gamma set, which is the intersection loci, where the sheets or the football orbifolds meet and intersect. So we will have, and we'll really have three different copies of this gamma sub z because um, due to the symmetry of the intersections. So the gamma set can be defined as the pairwise intersections of the orbifolds, written like so. And as you can see, we can decompose gamma into three coordinate planar kind of subgraphs, if you want to call them subgraphs, but they'll really have more analytic structure uh, in general in the case that we're interested in. So we're going to define a object that packages all this stuff together, this geometric information, and we'll call it the seed, which is a package of the main objects we've been looking at. A seed is just a triple of the underlying geometric scaffolding, the intersection locus, and a symmetry group, a finite symmetry group, acting on the scaffolding, MathCal I, by stratification, preserving orbit space automorphisms, and it's going to preserve uh, the orbifold orbit space, MathCal I. So the seed contains two natural spectral regimes. One, we can look at the cone points. So there's going to be 8 total cone points in this case. These are the cone local spectral data coming from the orbifold, neighborhoods of its cone points. Number 2, the incidence stratum gamma. This carries the global winding data, the global spectral data arising from the intersections of the orbifolds and from the pi equivariant compatibility conditions imposed along the common intersection locus. So gamma is not exactly an auxiliary graph. It's the invariant skeleton where the cone local data of the four orbifold sheets are compared, glued, and globally organized. So next we're going to analyze the cone points of the seed. So the foundational work of J. Cheeger, he did some foundational work on the analysis of cone manifolds, and this will be useful for us in the exploration. We can analyze the regions local to the cone points and see that this notion of a link factors into radial and angular components. So the link defines the spectral content of what we're going to analyze here. So first we'll look at one spindle orbifold F, not the entire MathCal I at once. So this is a short, brief sketch of a derivation. Let F be a football orbifold like we had, with two conical points, each having the same cone angle. We can near a cone point, the metric has the usual cone behavior. And we can put a flat unitary rank one bundle um local system of we can add holonomy if we want to, but we don't necessarily need to. But I'll show that once we forget all this holonomy, then we recover what we want. So along the azimuthal directions section satisfy this relationship, and we obtain a Fourier block decomposition. If we solve this, if we solve the radial equation, uh, we basically we have to do we have to do a Helmholtz like equation, the eigenvalue equation, and if we solve that, we get Bessel solutions, where the order is like so. If an orbifold isotropy condition restricts angular modes to a residue class, that then the theta kernel is this form. So Poisson summation gives the modular inversion, and in the untwisted case, or if we set these parameters to q equals 1, r equals 0, var phi equals 0, the Mellin transform recovers the usual completed factor, um, the gamma factor, or the lambda of S function, which is standard in the analytic number theory world for the derivation of the completed zeta function. So this is relatively standard. It's just the usual derivation of the completed factor, but we've just gone about it in a slightly different way, a more uh, geometric analytic way. So this shows that we can recover the classical Riemann factor for a um, single football orbifold. Next, we'll use the theta reciprocity to toggle between high energy modes. These are the cone local modes to low energy modes, which we'll see to be gamma. Then we'll consider maps. This is further along, but we'll consider maps, involutions of S, involutions of the seed, which send cone points to themselves and gamma to itself. The central theta reciprocity principle for the seed is that the cone local theta expansion and the global skeletal theta expansion are in fact dual descriptions of the same equivariant spectral datum. So we just say that this is basically just theta reciprocity, but we're interpreting it in a more geometric context, where theta sub cone of T denotes the cone local expansion on the orbifold sheets of Pascal I, while the right-hand side denotes the global expansion along the skeletal stratum gamma. So the idea is to take the pi orbit average at the theta level, that is before the Mellin trace, and then take the Mellin trace over this orbit average to collapse everything to the scalar completed factor. The theta reciprocity relation induces the usual functional equation involution on the Mellin realization. That's that S maps to 1 minus S symmetry, the completed zeta function. We denote this induced involution by map from the realization of the seed to itself, where I squared sub theta equals the identity, and R of S is just this some notion of the theta Mellin realization of the seed. So the theta reciprocity is a local analytic swap of spectra from high energy to low energy, and the zeta S maps to S 1 minus S symmetry is a global map from the seed to itself. So now we need a localization principle. We need something that says the non-trivial zeros can only be supported on gamma, for example, or some other stratum of the seed. What we can do is take the decomposition. So we decompose math chi. We decompose it into its regular part, and then its gamma set, and then its cone points. So we decompose it into that triality and show that the regular part and the cone points can only be holomorphic units, respectively. So once we exhaust those two as holomorphic units, this essentially localizes the support of the non-trivial datum of zeta to the particular stratum gamma. It essentially isolated everything to all the non-trivial information to gamma. So the Riemann hypothesis is then equivalent to the statement: is the spectral realization of gamma the critical line real part of S equals 1/2?